It took about 2 hours, 30 minutes.
So you just sat there and kind of stared and calmed down, like, well, it's time to wake up. Get going now. Y'all was trying to make me feel bad.
You should feel very bad.
Oh, what you trying to say?
I'm sorry that.
So in this section, we're going to look at doing some trig integrals that we haven't done before. We've integrated sine, cosine, tangent, secant, cosecant, cotangent, secant squared, cosecant squared, cosecant, cotangent, secant, tangent. But here we're going to do some integrals that have combinations of sines and cosines and combinations of secants and tangents. And on page 524, they kind of list some guidelines. Some of these will have an odd number of sines and an even number of cosines. Some of them might have an even number of sines, an odd number of cosines. It could be that you end up with an even number of both or an odd number of both. So there are different things you do depending on which one you have. Now, for this one, notice if we let u be cosine, what would du be? Yeah, negative sine x dx. So basically, we have u to the fourth cosine u, so u to the fourth. That needs a negative. Put one there and one there. Negative sine x dx. That's du. What's that integrated into? Sure. In terms of cosines, u is cosine, so that'd be cosine to the fifth x over 5. Let's see. Even if we change that problem just a little bit, let's change it to sine cubed so that we still have an odd number of sines. Let's see. Make sure I say this correctly. So if we're wanting to let u be cosine, then du needs to be sine. So we need to keep one of these sines for our u. So let's break this up. Let's call this sine times sine squared cosine to the fourth x dx. So just keeping track of things, if we were to let u be cosine, then our du would be negative sine x dx. So we need to keep one of those sines for our du, but let's change the rest of the sines into cosines. Well, remember that our Pythagorean identity is sine squared plus cosine squared equals 1. Or if we solve that for sine squared is 1 minus cosine squared. So where we have a sine squared, let's change that to 1 minus cosine squared. Let's rewrite this just a touch. Let's move the sign over with the dx. And then let's multiply this together. If we distribute that cosine to the fourth, we'll have cosine to the fourth x minus cosine to the 6x. That's actually, we could distribute that sign and call that the integral of cosine to the fourth sine x dx minus the integral of cosine to the sixth times sine x dx. Both of which u can be cosine in du negative sine x dx. So if we need a negative with our sign, put a negative out front. Same on the second one. If we need a negative sign, we can put a negative there, a negative out front, which will make that a positive. So basically we have a negative, that's u to the fourth, negative sine x dx is du. Here we have u to the sixth du. So that integrates into negative u to the fifth, so cosine to the fifth, over 5. This one would be u to the seventh over 7, so cosine to the seventh over 7 plus c. So an odd number of signs, we're going to keep one of those signs to be our du and change the rest of them to cosines. Let's do the same thing where we have an odd number of cosines. Let's say we have cosine to the seventh x, sine to the sixth x dx. Let's pull out one of those cosines and let's put it beside the dx. And then that will leave us cosine to the sixth. So that cosine that we save, that's going to be part of our du. So we're going to change everything into signs. Notice if u is sine, what is du? Cosine x dx. So that one cosine, we're going to leave it as part of our du. Everything else will change to sines. We've got sine to the sixth. Let's take cosine to the sixth and change it to sines. Real quickly, we've got cosine to the sixth. Our Pythagorean identity, if we solve this for cosine squared is 1 minus sine squared. Well, that's cosine squared. How do we get cosine to the sixth? Raise it to the third power. If we got cosine squared and we need cosine to the sixth, we need that 3 times. So cosine to the sixth. Let's see, if we square that, we would square the first, twice their product, the second one squared. That's squaring it. Now we need to multiply that out one more time. You'll see what I did there. I've got to cube that, so that's 1 minus sine squared times 1 minus sine squared times 1 minus sine squared. If I multiply two of those together, we get this. Just use the shortcut for squaring. 1 squared, sine squared squared, the product, that'll occur twice. Then we're going to take that and multiply times that. So if we distribute 1 times 1, 1 times sine squared. 2 minus 2 sine squared times 1, minus 2 sine squared times minus sine squared. Sine to the 4th times 1, sine to the 4th times minus sine squared. So that gives us a 1 minus 3 sine squareds, 3 sine to the 4th minus sine to the 6th. Okay, there. So that's what we're going to replace cosine to the 6th with. So cosine to the 6th changes to that. And remember that cosine x dx, that's going to be our du. So if we distribute our sine to the 6th, we're going to get the integral of sine to the 6th x minus 3 sine to the 8th x, 3 sine to the 10th x, minus sine to the 12th x times cosine x dx. So our u is still sine, du is cosine x dx. So basically we have, if u is sine, we've got u to the 6th minus 3u to the 8th plus 3u to the 10th minus u to the 12th du. So when we integrate that, that'll be u to the 7th over 7. So sine to the 7th x over 7. 3u to the 9th over 9. So when we do that to the 9th, that'll be sine to the 9th. When we divide that by 9, 3 over 9 will reduce to 1 over 3. 3, u to the 1 greater power, so 11 sine to the 11th x over 11, sine to the 13th x, and then plus 6. So odd number of sines, we keep a sine, change the rest into cosines, and odd number of cosines, we keep it a cosine, change the rest to sine. But pretty much, since we have it, if we have an odd number, we pull one out, we're going to have an even number left. If we have an even number, we can write that as either a sine squared or a sine squared to a power. Cosine squared or cosine squared to a power. Now, the third case is when neither one of them are odd. It could be that they're both odd. If they're both odd, you just basically pick one. Okay, I'm going to keep a sine and change everything else to cosines, or I'm going to keep a cosine and change everything to sines. But if they're both even, then we're going to have to use, excuse me, one of our identities. It's a power reducing identity. It actually comes from the double angle identity. Sine squared. Remember, one way of writing cosine 2x, the double angle identity, is, what's that? 1 minus 2 sine squared. If you were to solve that for sine squared, you could get 1 minus cosine 2x over 2. Sometimes that's called, I believe, power reducing, because on the left we have sine squared, on the right we have cosine. Now it changes the angle. And I could have the wrong name for it, too. But that is one thing it does. Cosine squared is similar, except it's 1 plus cosine 2x over 2. Now, if we had sine to the 4th and cosine to the 4th, we could still use these. We would just need to square our identities. If we had sine to the 4th, we would square 1 minus cosine 2x over 2. Or if we had cosine to the 4th, we would square 1 plus cosine 2x over 2. So if we replace sine squared and cosine squared with this, what do we get on bottom? 4. So basically we could pull a 1/4 out. Now let's distribute. We distribute, we've got 1 times 1. 1 times cosine 2x minus cosine 2x times 1 minus cosine 2x times positive cosine 2x. Make sure I'm doing this right. So those cancel. That gives us 1 minus cosine squared 2x dx. And what they say is once we do that, once we use these identities, we want to continue to use them until we end up with an odd number of cosines. This first part, we can do this integral. But here we still have an even number of cosines, don't we? Let's use this identity again with this. Our identity again was that cosine squared, and let me change our letter. Let's call it cosine squared theta. It's 1 plus cosine 2 theta over 2. So In our case, we got cosine squared 2x, so what is our theta? 2x. So we're going to change this to 1 minus cosine twice theta. Well, if our theta is 2x, what would twice theta be? 4x. Yes. Over 2. So notice we have a 1 minus 1 over 2 minus cosine 4x over 2. Dx. All of these are things we can integrate. 1 minus a half, that's a half. We can pull a half out here. Call that cosine to the 4th x. So 1/4 times, let's break this into two separate integrals. The integral of 1/2 dx minus 1/2 the integral of cosine to the 4 cosine 4x dx. What do we get for this first integral? 1/2 x. Or we could call it x over 2. How do we integrate this? Yeah. So u is 4x. So what's du? 4 dx. So we've got cosine u. We need du, so what are we missing? The 4. So that's du. So if I put a 4 there, we've got to put a 4 on bottom out front. So minus 1/8 the integral of that's cosine u du. What's the integral of cosine? Sine. U is 4x. So we want to get rid of those brackets. Distribute the 1/4. Get x over 8 minus 1 over 32 times sine 4x. 1/4 times c, that's just a constant, so plus c. That's messy. But if you have an even power for both sine or cosine, or if you just have one of them, just sine or cosine with an even power, then we're going to have to utilize at least one of those. Unfortunately, when we utilize those, we still ended up with an even power for our cosine. So to handle that, we use our identity again. If we replace that again, we get cosine to the first. We get an odd power for cosine. Once we get there, that's going to be something that we can deal with. And the thing about some of these trig integrals, there are sometimes more than one way to do it. There might be a different substitution that you would see. But this is just kind of a customary one. All right. So that's dealing with sines and cosines. Let's look at some that have secants and tangents in them. Let's see. We know that the derivative of secant is what? Yeah. And the derivative of tangent? Secant squared. So in dealing with secants and tangents, we're going to have to keep these in mind when we're picking our u's and our d's. So let me see if they've got one. Let's do something like tangent to the fifth, secant to the fourth. Page 527, they list a couple of different cases. The first case is if secant is even. The second case is when tangent is odd. The third one is when there are no secants, and the last one's when there are no tangents. So let's see. I guess we can look at this a couple different ways. Sometimes there's more than one choice you can make. Because 1 and 2 both actually fit. Here, secant's even. That's what you use for step 1, or option 1. Also, tangent's odd. That's the option you use for the second one. So let's do it using the first option. They said if we've got an even power of secant, then we're going to pull out a secant squared, and that's going to be our du. Which would make our u tangent. So if we have an even number of secants, we can pull a secant squared out, so u would be tangent, thus making du secant squared. So we've got tangent to the fifth. If I borrow 2 secants, then I have 2 more here. Now, since our u is tangent, we want to change all of these to tangent, so that we have u's and then du. Well, we had a Pythagorean identity for that. Remember, sine squared plus cosine squared was our first Pythagorean identity. But if we divide it through by cosine, we got tangent squared plus 1 was secant squared. So that was another one of our Pythagorean identities. So in place of secant squared, we're going to put tangent squared plus 1. Now if we distribute here, we're going to end up with tangent to the 7th plus tangent to the 5th times secant squared dx. Remember, we're going to let u be tangent, so du is secant squared. dx. So basically we have u to the 7th plus u to the 5th du. We integrate that. Got to integrate to u to the 8th over 8th. So tangent the 8th over u to the 6th over 6, which so tangent to the 6th over 6th plus c. So it's just going to be keeping up with, okay, how many secants do I have? How many tangents do I have? What do I want my u to be? What do I want my du to be? Let's see. I said that we also could have used our second rule for that, where we have an odd number of tangents. Let's see how that works. If we have an odd number of tangents, we're going to pull one of those tangents out. And we're going to change everything else to secants. Because remember, if u is secant, what's du? Secant tangent. So we're going to take one of these tangents out. We're going to change everything to secants. Well, if our du is secant tangent, we also need one of these secants. So let's take one of these secants out and move here. So that would be what, secant cubed? So secant tangent, that should be dx. So if this is du, if we can get all of these to be secants, then we're going to have secants, so u's du. So since we have now an even number of tangents over here, tangent to the 4th, remember tangent squared plus 1 was secant squared, so what's tangent squared? Subtract 1 from both sides, so secant squared minus 1. So how do we get tangent to the 4th? Raise both sides to the 2nd power. So tangent to the 4th is secant to the 4th minus 2 secant squared plus 1. So tangent secant to the 4th minus 2 secant squared plus 1. Now we're going to leave that as our du, so we want to distribute everything else. So that's secant to the 7th minus 2 secant to the 5th plus secant cubed, and then our secant tangent dx. So just remember, u is secant, so du is secant tangent. So this is u to the 7th minus 2u to the 5th plus u du. So that integrates into what? U to the 8th. So secant to the 8th over 8th. This would be minus 2 secant to the 6th over 6, which that reduces, plus secant to the 4th over 4 plus. So it's a little time consuming, but if you can pick up on the patterns, it's just knowing, okay, an even number of secants, then I can pull out a secant squared from my du, change everything to tangents. An odd number of tangents, I can pull out one tangent, one secant, let everything else be secants. Now, we did the same problem twice. We integrated the same thing twice, but notice our answers are not the same. But they are equivalent to each other. If we took this one and changed it into secant squareds, we would get that.
Oh, the second one, when you take out the tangent, why don't you the tangent?
Because what? We need something for du that the rest of it would be u. So if du is tangent x dx, what function has a derivative of tangent? I'm not. It's actually negative natural log absolute value of cosine, which we don't have that. So that's why. It goes back to, did I write? I think it's here, that the derivative of secant is secant tangent. So, and the derivative of tangent is secant squared. So either we need that for our du, because the integral of this is secant. If du is secant tangent, that makes u secant. Or if du is secant squared, that makes u tangent. So we need one of those to be our du, because we know what function that's the derivative of. So we don't have an option of having just secant as our du or just tangent of our du, because just secant's not the derivative of anything, and just tangent's not the derivative. I mean, yeah, technically it's the derivative of natural log, but we're not doing it. Does that help?
So I guess you could, it's just a lot harder.
I mean, you could, but it's not going to fit what we have. Because we didn't have a natural log in our problem. And if du is tangent, that means that u would have had to have been that. We don't have on x to be argued. Yeah. So a lot of it is going to be just knowing these patterns. The patterns from 527 and the patterns from 524. Now there's just like one other type, and I don't know that I'm even going to assign any of these, but the last thing on page 529 deals with, well, what if we have a product of sines or cosines that have different angles? Like sine 2x times sine 3x, or times cosine 3x dx. Well, if, let's say, this was 2x and that was 2x, then we could have let u be sine 2x, and du would be the derivative of that, which is 2 cosine 2x dx. But if that's 3x, then we don't have a match. So if these are different angles, we actually have to use an identity. And you may remember from trig that if we have a product of sines or a product of cosines, I'm trying to think the way we did it in trig. Ours was something like, if we have this, it comes out to 1/2 sine alpha minus beta plus sine of alpha plus beta. Does that sound a little familiar? When we did that chapter on identity. So if we have sine of two different angles, we could write this as the integral. We could bring our 1/2 out front and call that sine of the difference of those, 2x minus 3x, plus sine of the sum of those. Well, both of those are things we can integrate. If we integrate that, we just let u be negative x, so du would be negative dx. When we integrate that, we let u be 5x, so du is 5 dx. So we just do a u dx. So that's kind of the other case that we deal with in 8.3. So I know over the 4th of July, that opportunity